Okay, so good afternoon, everyone.
Good afternoon.
So should we start or wait? So normally, how many students attend? Okay. Okay, so let's start then. So welcome to this course on electromagnetic theory. So I will start with electromagnetic theory and then I will continue to electrodynamics later on. So today the topic will be related to electrostatics. Okay, so before I start, so I'll just give you a bit of a introduction or idea, like what we will be basically dealing with in this course. So when you look at physics in general, so the idea is to understand how things work in at different dimensions and when they are stationary or when things are moving. So what are the physical principles or what are the principles that decides or determines how a particular system behaves? So in that sense, we have basically classified our the domain of physics into broadly four categories. So one I could say uh, is like right? So one I will say as a classical mechanics. This is where we deal with or apply the Newton's laws of motion, and typically it deals with objects which move with a speed much less than the speed of light, and typically the size will be quite large, so which is like of the order of like few millimeter up to few thousand billion meters. So that is the size that we are looking at when we are applying this classical mechanics. So the size can be, let's say, the dimension would be the order of more than, let's say, so in terms of meter, I would say 10 to the power minus. Then what we, uh, but if let's say some objects which are moving at a speed of light, for example, so then we need to change Newtonian mechanics is not anymore valid. So when your velocity or the speed is comparable to the speed of light, so in that case we go into a domain which we call as a relativistic mechanics, which we use what Einstein proposed. So then the classical mechanics or the Newtonian mechanics failed, and we have to adopt relativistic mechanics and those formulations to understand the physics in that domain. So in the same sense, like if I now go to a very small dimension, for example, to the size of molecules or atoms or few molecules. Okay, so where the size is of the order of 1 nanometer or less, let's say, typically of that order. So there again, the Newtonian mechanics does not give us the correct result. So we have to refer to quantum mechanics in that case. This is what you have been already introduced. And then there is also a region where things are in smaller dimension and the speed is comparable to the speed of light. So this is where a very different kind of mechanics is used, so which is called as a quantum field theory. So these are like basic, I would say, the the mechanics that are used in physics to understand objects at different length scales and objects which are moving at certain speeds. Now, so corresponding to these four realms or four uh, parts of physics, so there are also four fundamental forces. So forces are four fundamental interactions that also we have so far identified these four fundamental forces, which are quite distinct from each other. So one is gravitational, then there is electromagnetic, then there is weak force, and then there is a strong force. Now, as you must be knowing that the gravitational is like what we experience, the universe, the galaxies, the planets, the sun. So all these motions, so astrophysical objects, so they experience this gravitational force. This is what is it's part of our universe. Mhm. Then electromagnetic force, which is basically all our electric field, magnetic field, or whatever we encounter in on Earth, most of that is actually a consequence of an electromagnetic force. Everything will be part of that. Then when you go to a smaller dimension, like you go to atomic or even subatomic particles, so in that case, you have the weak and strong force, which which can be only realized within a nucleus, or even you go to further break this nucleus. So now, for our everyday experience, either we experience gravitation or electromagnetic force or electromagnetic interaction. But when you look around yourself, all of the applications that you see, so most of them are based on this electromagnetic forces. So whether you operate a computer, a laptop, we are doing a online this uh, learning through interaction, a mobile, WhatsApp, everything, what you look around. So it is all about electromagnetic interaction. In fact, so I have, if I ask you, like, what about, let's say, a friction, for example, or molecular forces, or chemical forces, which cause a chemical reaction, for example. So what are they different? Are they part of these four fundamental forces? They are. They have to be, because this is what we have defined, these four fundamental forces. Then if
Sir,
I,
your screen is
what
not
is
visible.
friction? Yes,
Sir, your screen is, yes.
screen is not visible.
Yes, sir, now it's visible.
Visible, sir, visible.
Now visible?
Yes, sir.
Okay. So friction or molecular force or a chemical force. So what are these forces? So these are also part of your electromagnetic force. So if you look at in a fundamental level, so these all chemical reactions that happen, it is a form of some charge carriers that are moving and interaction of charges that are stationary or they are moving. So this is like electromagnetic in nature. So even molecular forces, these are all like how a molecule forms, for example. So that is also part of an electromagnetic force or electromagnetic interaction. These are all based on a Coulomb interaction. So we'll see, we'll start with that. And in electromagnetism, another thing which is also very important. So when we talk about electromagnetism, so the basic idea what we want to understand is we have a distribution of charges. Okay, so these are what I am drawing. These are all charges. Now, how these charges affect any other charge, okay, which is at a distance, which could be at a certain distance, s or x or whatever you want to call it. So it is at a certain distance s. So how these charges, distribution of charges, or even one single charge, how that affect any other charge which is far from it or away from it at certain distance. So this is what basically electromagnetism is all about. Now, to understand this, so we will go stepwise. So first, what we will do is, let's see what happens when charges are constant. So they are not, so these charges which we are talking about, they are stationary. Okay. So how that will affect any other charges, for example. So this is what we call as electrostatic. Okay, so this is the first thing what we will deal with in today's class. Then the next step is these charges will be in motion, but with a constant speed, and it will create something which we call as a steady state flow. So we'll talk about that later. So steady state flow, which will result into a current, electric current. So now, due to this current, so what you have is basically a magnetic field. So that we will deal with in a part of magnetostatics. Okay. So the next step is now these charges. This is not a steady state flow. So the charges can move arbitrarily. They can have non-uniform motion. They can have acceleration. So that will result into something what we call as electromagnetism, or it will be part of what we call as electrodynamics. Okay. And in each of these discussions, so we will still be in the realm of, or in a physics realm that I discussed earlier. So we'll be still in the classical domain. Okay, so we will not really go into any quantum mechanics or relativistic mechanics. So we'll always, so maybe in the end, we will look at a bit of a relativistic effect, but mostly our discussion will be in a classical domain. Okay. So what we are dealing with, so we'll be dealing with electrostatic, where we are talking about how a stationary charge, it affects another charge. So charges, basically how many charges are there? So there are two types of charges, right? So one is a positive charge and one is a negative charge. This is what we have in nature. So one is a positive charge and a negative charge, and mostly, so the charge is, it is quantized. So the charge value, so if I go to really the smallest particle that I have, that exists in, that we can really see in nature, so which is the electron. So we'll have a negative charge. This is electron. So you have then proton, so which has a positive charge. and so on. So these are all like a particular number you have. So this charge corresponds to 1.6 into 10 to the minus 19 coulomb. So this is a unit of charge. So one can be a positive charge and one can be a negative charge. Now, if you put both two charges together, so they will cancel each other out. Now, what we are interested in understanding how one charge, it could be a positive charge or negative charge. So how it will interact with another positive or a negative charge, how it is going to interact. So that means, there is no physical interaction like the forces that we know, let's say in mechanics. So you have to either push or pull. Okay, so that means you are really involved in the process. So there is a physical contact between what you are doing. But in this case, there is no such physical interaction, physical contact between these two objects which are interacting. So they need certain, there should be a certain medium to which they will interact. So that medium, what you call as a electric field. Okay, so what we can say is like a charge spreads an electric field. So like you sprayed, it is like a smell of something. So now another charge, which is somewhere nearby or maybe somewhere, so it can smell this the electric field, and that is how it will interact with that other charge. Now, depending on how far this charge is, so the smell will be stronger or it will be weaker. So that means if the charge is too far away, so the electric field will be weaker, so the interaction will be weak, or the force will be weak. And if it is nearer, so the interaction will be strong. So the smell, let's say if you have put something which has a smell, so you can smell it easily if you are nearby. So something like that is happening here. So this is what we call as an electric field. So you have electric charge which produce this electric field, and through this electric field, so they will interact with other charges. So which can be understood in terms of like, we can write some forces, like when we talk about interaction, we can write it in terms of fields. And interestingly, what we will do in this case also, we will write it down in terms of potential, which is different from potential energy. And then also there will be some energy as well. So these are the things which will be used in understanding this interaction. So when we want to understand this electromagnetic theory and then electrodynamics, so there are four famous equations which actually capture all these interactions in a very simple way. Okay, so these are called as a Maxwell's equation. So we will talk about that later on, but I will just want to introduce you to these equations because they will be really useful, and you should be doing it like from the day one. So there should not be any, or at least at the end of the course. So if you can write down the Maxwell's equation, I'll be writing down those equations. So if you can write down those equations and explain what they are, so you will be a master in electromagnetic theory. So what are the equations? So there are two sets of equations, okay, and each set contains four sub-equations, let's say. So let me first write down what is like a general equation. So the first one, what we call as a del dot E, or a divergence of E, is equal to rho by epsilon naught. So rho is here the charge density. So charge density as density means something, let's say normal mass density will be mass by volume. So here charge density will be charge by volume. Epsilon naught is the permittivity of the space. Then the second equation is curl of E equal to minus del V by del T. So this is what we call as this symbol, what we are writing, we call as a curl of E. That is minus del V by del T. So this symbols, what this del symbol that we are writing with a vector sign. This is also very important. So you have to keep, these are all vector equations, so they are not scalar equations. Okay, so then there is del dot B, which is equal to 0. Then the fourth one is curl of B is equal to mu naught J plus mu naught epsilon naught del E by del T. So these four set of equations generally, so these are called as the general Maxwell's equation in vacuum, and they capture everything that we are going to discuss in this. So some of these are written in something what we call as a differential form. So this operator, like what you are seeing, the symbol del, so we call it as a del operator. So we are operating this on a function. So this is an electric field. E stands for electric field, for magnetic field. So it operates on that and creates a different scenario. So as I said, rho is the charge density. So similarly, J here. So J here is your current density, the volume current density. So mu naught is the permeability of free space, and B and E stands for the electric and magnetic. So similar equations also exist in a matter. So if I take in a matter, so this, then there are four such set of equations. So del dot E, or the divergence of E, is F, then curl of E is equal to minus del V by del T. So that equation is not going to change. The third one is also not going to change. Only thing, the first and the fourth will change a little bit. The symbols are changed because there will be some new meaning that will be coming up here. Otherwise, the things are similar in the matter as well. So rho F here, the free charge density. So D is the displacement vector. So which is normally written as epsilon naught E plus P, where P is your polarization. And H here is given by B mu naught minus M. So M is your magnetization. So because when we talk about a matter, so you can have a polarization or you can have something as a magnetization in a matter. So that's why these two terms have been introduced. However, those four equations will still be there. So if you can explain, write these equations and understand these four equations well, so you then understand what electromagnetic is. Okay, so one thing which now I have written these four equations, but I have not really explained anything about it. So we will look at one by one. So one thing is the physics that we are talking about is not only about writing equations. It is about writing equations and understand the equation. And understand, moreover, you need to understand without really solving them. So is it possible, like your approach when you want to understand something is like, okay, I wrote an equation. Can I understand what the physical meaning of this equation or what it wants to convey without really solving that equation? That should be the first thing you should do. Of course, if you solve, you get better insights, more insights or understanding of what is that physical principle is, how it operates, and what are the conditions where it's valid. Okay, so those things you get a better knowledge about that. So solving those equations is important, and therefore knowing some tools which will help you in solving those equations is also important. So you need to know some tools, and in physics, those tools are nothing but mathematics. Okay, so we have to use some mathematical tools to solve this equation so that we can understand it better. And there are two other things which are also very important, really crucial in electromagnetism. So one is the coordinate system. Okay, so whenever you are solving something, so you have to define the appropriate coordinate system, because without that, so since we are dealing with vectors, so we need to properly define the coordinate system. And then normally, not only one type of coordinate system, so we'll be using three types of coordinate systems. One is, of course, which you are familiar with. So this is very important here. So one, of course, you are familiar with is a Cartesian coordinate system. Then there is a spherical polar coordinate system. And then there is a cylindrical coordinate system. So these three coordinate systems we normally use in electromagnetism. And the choice of coordinate system depends on what kind of problem you are dealing with. So sometimes if you have, for example, if you have a spherical symmetric distribution of charges, so it will be suitable or appropriate to use a spherical polar coordinate. So Cartesian coordinate system will be very difficult to solve those equations in those coordinate systems. So similarly, if you have like talking about a wire or a distribution on a needle, okay, so that kind of situation, the charge distribution on a needle, for example, or on a wire, or on a micro wire, for example. So in that case, it is appropriate to use a cylindrical coordinate system. That will help us or help in simplifying the problem and solving it much faster. And then another thing which we should be careful about, the operators. Okay. So in quantum mechanics, you might have done a lot of operators. So here, the common operator that we are going to use is del. Okay, so this is a vector operator. Okay, so you should be very careful when you are using this del operator on any function. Okay, so this is a vector operator. So that means it will have three components, so not one component. So this is very important. Then another thing is, of course, units. So we should be very careful about which units you are using, CGS or SI, because the formula will change completely if you are using a CGS or a SI unit. So in this course, we will stick to only SI unit, so not a CGS unit. But sometimes in some books, CGS unit is used, which can change the equation quite a lot. Okay, so I'll just put a quote from Dirac just to summarize what we just discussed here. So Dirac was a famous physicist. So what he was always interested in, he was like of the opinion that if I can understand what an equation means without really solving it, actually solving it, if I can find out what are the characteristics of an equation, what is the physical significance, physical insight of an equation without really solving it. So then I know that I understand what it means. Okay, so that is what his opinion was, and I think this is actually correct, that we should not focus too much on doing a mathematics and solving the equation. That is important, but you should be solving or like understand the equation without really solving. And another interesting thing which I just want to add here, this electromagnetic theory is really a profound theory, particularly this Maxwell's equation, for example, which, if you look at how it has impacted our development, it is immense. Okay, so starting from 1850s onwards, so we have electricity, then magnets, then electromagnets, and so on. So starting from those days until now, so all applications that we see in our daily life can be solved using those four Maxwell's equations. Okay, so this is what Feynman, another physicist, who said long back. So he said, let's say 1,000 years from now on, okay, so if somebody after 1,000 years look at the history of our civilization, so, and if you look at what is the significant contribution of the event that happened in 19th and 20th century, so it will be the Maxwell's laws of electrodynamics, nothing else. So it is not about the World War, the World War I or World War II or whatever happened, but it will be basically the contribution of Maxwell's that will be actually considered as one of the most significant contribution to the human history, because that is how it has contributed for the development. Okay. Okay, so this is a little bit of, we are going off from the discussion. So let's now come back to for today's class, that we will basically talk about the electrostatic part. So that means we have charges which are stationary, and we want to see how a charge affects the another charge, for example. Okay, so this is again, so you are all familiar with that. So let's say if I have two charges, Q1 and Q2, so the forces between them, I can write, this is again a vector. So this is where it is very important. So you should be using the vector notation. So Q1, Q2 divided by R square and R cap. So this is a unit vector. So this vector which joins these 2 points. So point, let's say this is the distance R between these two charges. So this is what you know, the Coulomb's law. Okay. Okay, so before we talk about this electrostatics, I said I need to introduce some of these mathematical tools that we are going to use quite extensively in this course. So the first thing what we talked about is this operator, which we call as a del operator, and this is a vector operator. So now I can operate it on a scalar. Okay, so this I can operate it in a scalar. So what we call it as a gradient of a scalar. So how it is written? So del is normally in a Cartesian coordinate system. So it is given by x cap plus del by del x, y cap del by del y, plus z cap del by del z. So these are what we have is like this partial differential equation, del by del x, del by del y, del by del z, partial differential equation, and this is a vector operator. So now if I operate it on a scalar, so I have something like this. So here S is basically a function of x, y, z. Okay. So you will get some value which is a vector. So I'm operating a vector operator on a scalar, but the result, the output, what I will get is a vector. So this is, you should be very clear about. So you should not have any confusion. So when you are operating del on a scalar, you will get a vector. Okay, so this is one thing. So there are some other identities that are associated with this operation, so which you will find in other mathematical physics book or in a standard book on electromagnetic theory. Then there is another. Now this del being a vector operator, I can also operate it on it. Oh, sorry. So I can also operate it on a vector as well. Okay, so not only on scalar, so I can operate it on a vector as well. So let's say if I take a vector, so I must introduce this dot product. So I cannot just put del, I cannot just have an operation like that. So I have to put it as a dot product or a cross product. So either it will be a dot product or a cross product. So these are the two operations I can do using the del operator. So if I operate this on A, so again, you can write it explicitly this form. So you need to practice all this a little bit so that you can write it immediately. So now this is a dot product between a del operator and a vector. A vector has three components. So here x cap, y cap, z cap are the unit vectors, and in this case ax, ay, az are the components of the vector along the three component Cartesian component. So what I will get is, so del ax by del x, del ay by del y, plus del az by z. So what do I get if I operate this operation del dot a? I get a scalar. This is also interesting. Okay, so this is also you should be clear about. So it is not anymore. So I'm using two vector operator. I'm operating a vector operator on a vector. So del dot a. So like you do two vectors, you take a dot product, it will be a scalar. So that is what we get. So similarly, you can also operate this del cross a, which we, so this del dot a you call as a divergence. Okay, so let's just a little bit look at this divergence in more detail. So because this is again a mathematical tool we are using or will be using quite often when we want to understand how electric field and magnetic field behave. So we have this divergence operator. So what it means, there are various interpretations or understanding. So one interpretation, mathematical interpretation, is like what we have done here. Then there is a geometrical interpretation. So a geometrical interpretation means that if I have a vector A, for example, so the divergence means how it spreads from one point, so how it spreads in a region. So that is what this divergence will say. So if I have some vector or a flow, for example, so how that flow, flow spreads. Okay, so how that flow spreads in a space. So that is what I can find out by using this operation. So mathematically, if I do this operation on a vector and I get some finite value, so I know that that vector spreads out in space. For example, if I have a vector, okay, so something like this. So you know how vectors are represented. So here the length represents the magnitude and the arrow represents the direction of the vector. So here the vector is a small vector. This is where magnitude is more. This magnitude is more. Okay. So this is say kind of a vector I am talking about. This A vector, for example. So it is spreading out from this point. So now if I do this del dot A on this, so I'll have a finite divergence. Okay. Now if I take, for example, a vector something like this. So each all have the same length in the same direction. So there is no divergence. Here the divergence of this vector will be, in this case, divergence of the vector will be not zero. Of course, it will be a scalar, but not zero. But in this case, this distribution, the divergence will be zero. Now, if I take a situation where is, let's say like this. So what do you think will be the divergence? So this length is even longer than the previous one. So is there a divergence or not? There will be a divergence here as well. Okay. So here the divergence of A will be. So this is where you will have. So you have to be pretty so careful when you are calculating this divergence. So one thing also I should tell you that there is no such thing as a divergence of a scalar. So that is never going to. You will never have such a situation where you can calculate the divergence of a scalar. So divergence will be always of a vector. So similarly, a curl will be defined like how you have defined a curl operator, like when you take a curl, x cap, y cap, z cap, then you have del by del x, del by del y, del by del z, then ax, ay. So this is how you calculate the curl of a vector. So the curl of a vector is basically tells you how much the vector rotates around a particular region. Okay. So this is what a curl would represent. So if I draw an axis, let's say something like this, and my vector I draw something. Let's take this color. So there is a rotation of the vector so about certain axis. So that means I will have a finite curl. So there is similarly a mathematical interpretation as well as a geometrical.
Hello. Hello. Anyone please reply?